Ready? What we're now going to do is use a practical students can do themselves in years 10 and 11 that precisely replicates the way that information from satellites is being used to better understand what is happening to the climate on Earth. It involves the measurement of ocean temperatures, and it also involves understanding thermal infrared emission. We know that every object in the universe, if it's above absolute zero in temperature, is going to be emitting electromagnetic radiation. And the main wavelength at which it emits that radiation will depend upon the temperature. We have certain black body radiation curves. It does depend upon what the substance is that's doing the emitting. But in simple terms, if we can measure the amount of infrared radiation being emitted by something, we can make a pretty good estimate, depending upon what that something is, of the object's temperature. And that's the principle behind one of these. What we've got here is an infrared handheld thermometer. These are used for measuring babies' temperatures, etc. They're specifically calibrated for a human being's thermal infrared emissions, which might differ from something else. And the way that they work is very simple. If I push the display, and I hold it about 3 or 4 millimeters from the surface whose temperature I want to measure, there we can see, I think we can see okay, we can see that my skin temperature is about 31 degrees centigrade. Now if I let go of this and I just point this upwards, I've now got an air temperature of about 25 degrees centigrade. Now I've got to be honest, with these they're relatively cheap, they're about 10 to 20 pounds each. There are some errors that will come in because these have been calibrated to measure human skin temperature, and so the air temperature itself in here I can tell you is not 25 degrees centigrade, but to be honest what we're going to be using these for are to illustrate the principles behind how we can use thermal infrared emissions to understand what's happening with Earth's oceans. Now what we're going to do is we're going to be using one of these with our groups, and you will see the video of Cardinal Newman students actually doing this experiment as an extra video along with this resource. And what we need to do first of all is we need to prepare our ocean, and what we're going to use is an aluminium tray here. It's a cold water ocean, so I've got some cold water here just out of the tap, so at about 20 degrees centigrade, and I deliberately use aluminium trays that have got a sort of crenellated, I forget the word, uneven bottom. In other words, we've got variations in ocean depth there. And I'm not pouring in too much water, I'm getting about 5 millimeters in the shallowest point, about 10 millimeters in the deepest point. So I've got my water ocean, I'll put in a little bit more. Now Europe's premier environmental satellite is a huge satellite called ENVISAT. It's the size of a bus and it's been orbiting the Earth for about 8 or 9 years now, and it's transformed our understanding of the oceans. ENVISAT has got a battery of instruments on board, but one of those instruments is called the AATSR, the Advanced Along Track Scanning Radiometer, and effectively what it is one of these, because as ENVISAT is orbiting the Earth 16 times a day, its AATSR is looking downwards and it's measuring the infrared emissions of the land, of the oceans, to make a really accurate estimate of what the temperature of those surfaces are. And it's accurate to about 1/10 of a Kelvin, 1/10 of a degree centigrade. So what we're going to do is we're going to use our handheld infrared thermometer to mimic what ENVISAT is doing on its orbit. Now of course ENVISAT would make one pass. What I'm going to do is take my piece of paper here and I'm going to split it into a grid of 3 by 4. And what I'm going to do first of all is the 3 by 4 grid here will correlate to various grids in the ocean here. And so what I'm going to do is I'm first of all going to measure the temperature, as ENVISAT would do, of Earth's oceans. And I've got 20.3 centigrade for this square. I've got 20.3 for this square, 20.2 for this square, some experimental error there. Of course, students will move it up or down, which could introduce some errors here. I wouldn't worry about that too much. Again, it's a principle demonstrator here. 20.3, 20.2, 20.2, 20.3 again for argument's sake. But we get the idea here, and I get the students to go along like this, and along like this, and along like this. Of course, ENVISAT will just do this in one continuous pass. What I'm now going to do is I'm going to introduce a source of warm water into the oceans. This is water that is pretty hot. It's about 70 or 80 degrees centigrade. I boiled it, in fact. According to this is actually at 62 degrees centigrade, so it's been cooling for quite a bit. And I'm going to pour in a small amount into one corner. A small amount, how much do I mean by that? Probably about 30 to 50 mils. So I pour my warm water in, and then I'm just going to stop. I'm going to leave it for a few seconds, and now I'm going to repeat the exercise. Again, ENVISAT measurements, and I've got 44.5 in the corner where I introduced the water. I do it over here. I've only got 33.2 over here. I've got 32.6, and so what I can get a very good measure of from the thermal infrared emissions is I can get a measure of how the warm water itself is starting to move through this cold water ocean. Now, humans are a very visual species, so what we would do with this data set is we would then colour code the temperatures. So anything, for argument's sake, above 40 degrees centigrade may come out as being very red, anything between 30 and 40 centigrade may come as being yellow, and anything less than 30 centigrade may come out as being blue, and I can get a single thermal image snapshot, a false colour image where the colour is used to give me a representation of what the temperature of the ocean was in that snapshot. Now, the way that TV pictures work, of course, is that you stack a load of these images one after another that were taken at certain time intervals, and what we can use for that is to have a dynamic movie that's effectively showing what is happening to the warm water areas within Earth's oceans. Now, this part, students are very happy doing the measurements, but it doesn't have that wow factor. As I said, we're a very visual species. So what we're now going to do is we are going to do a second experiment that shows the results of what will happen if we took lots of these individual measurements to make lots of individual thermal image snapshots, and we then put them together to get a moving dynamic image, and this is a lot more spectacular. What I have here is I've got thermochromic paper. So this is paper that will respond to temperature changes. And if I breathe on it, we can see there how, depending upon the temperature, it will change colour. Of course, different thermochromic papers are calibrated for different temperature changes within different temperature ranges. This, again, is basically a principal generator here. So what I'm going to do is I'm going to put the thermochromic paper. You could prepare a fresh, a new water ocean, but I'm just going to put it in the same one, and you sink it to the bottom of the ocean, dark side up. Now, at the moment, we've got the sheet being completely black. And Sophie, would you mind zooming in? And what I'm now going to do is I'm going to introduce my warm water, and what we'll see much more dramatically, we will see a visual representation of what is happening in terms of temperature differences in the water, and it will be real time, so it should be a dynamic image. Now, this is exactly what we would get if we stack together a load of separate thermal images of the ocean, obtained in the way that the students have done. So the second part of the experiments is the students will introduce some warm water, and you can see very clearly that we have dynamic flow of warm and cooler water here. And what I found with students is this is a bit of a eureka moment, because they've got the idea that there are ocean currents, but this really brings home to them that it's temperature differences within the ocean that are driving ocean currents. And of course, this is one of the reasons why, let's face it, in terms of the latitude we live at, if we look at the amount of radiation coming from the sun, we might think to ourselves, well, we should get the same sort of winter as they get in northern Canada. You know, the last year, 2009, 2010, certainly for most of our students, it's been the worst winter that they can ever remember. Well, why don't we get conditions like that for 4 months every year like they do in northern Canada? And the reason, of course, is the Gulf Stream. We've got a warm water current that comes up from the tropics and keeps Britain a lot more temperate than it would otherwise be. So once again, if I ask Sophie if we can go in. Now, this will work when we introduce warm water in. And yes, we have a wow factor, but it's a lot more than just Brainiac. If they want a wow factor, they can watch Brainiac, they can watch Mythbusters. Actually, Mythbusters does go into the science a lot better, I find. Sorry for the plug there. But of course, if I introduce cold water again, we get the same effect. Because whether it's warm or whether it's cold water, it is temperature differences in the oceans that are driving ocean currents. And once again, this is an analogy, it has got its limitations. So if we look specifically at what's happening in this tray, of course it is not the same exactly as what is happening in the Atlantic and the Pacific. But the fundamental principles are there. If we understand about thermal infrared emissions, if we understand about convective processes, then we can put those ideas together to try and determine what is happening in our oceans, what is the thermohaline conveyor, and potentially what is the effect of human behaviour and human activity. Is there an anthropogenic factor in understanding what is happening within our oceans?